This is the second video for section 16.1, and in this video we're going to look at multiplicity and behavior and how to graph some of these functions using that information. So the first thing I want to talk about is multiplicity and how that will affect the end behavior and intercepts of a graph. So multiplicity are when roots occur more than once. Technically this can also count for when they occur once, but then your multiplicity is just one. It's not happening multiple times. So what this is really saying is that you've got a root appearing more than once. When you have a root appearing an odd number of times, so it has an odd multiplicity, then we know that the graph is going to cross the axis. And again, this is the x-axis because we're looking at x-intercepts or roots. And if we have even multiplicity, so if that number is even, then the graph will kind of bounce. Some say touch, but not cross the x-axis. So if you think about a parabola, for instance, especially one centered at the origin, it's just going to kind of bounce and then go back up in the other direction, whereas odd multiplicity is going to cross through the axis. So let's take a look at some examples here. We want to find the intercepts and determine their multiplicity. And then we're going to determine what would happen to the graph then based on that multiplicity. So our first root here, x minus 1, would give us a root of x equals 1. And our multiplicity, we can just use capital M in this case. Multiplicity in this case, it only happens once. There's no exponent. And since that is an odd multiplicity, it will cross the graph, or cross the x-axis. And next root that we have, x minus 4 squared, that will give us a root of 4, which has a multiplicity of 2, because that's our exponent there. And since it is an even multiplicity, it will bounce or touch, whichever you prefer. And finally, we have x plus 8 cubed. So this is going to give us a root of negative 8. Again, we're doing the opposite sign. It has a multiplicity of 3, which again is odd, so it will cross the axis. So if you were kind of just in general looking at your graph, the other thing we can tell about a graph is if our lead coefficient, which in this case would be a positive 1, if it's positive, because this is positive, positive, positive x, since all of those are positive, and this is actually a polynomial of degree 6 because we've got a 1, a 2, and a 3. If we add those together, we get a degree 6. We know that this is going to have a general kind of parabolic shape with maybe a wiggle in the middle. So we know that our graph is going to cross at 8, do something in between. We didn't find our y-intercept. Our y-intercept in this case would end up being a rather large number, a large negative number. So it would come down to whatever that is. And then at 1, it would cross again. So it would come back up at 1 and cross. And then it would go up and it would bounce at 4 and keep going up. So it would look something like this. Again, it's not a real good graph, it's just kind of a crude estimate of what it would look like. So I want you to pause the video here and try example 6. So for example 6, you should have found your roots were 0 with multiplicity 3, which means it's going to cross, and negative 12, which has multiplicity 1, which is also going to cross. And again, this is just kind of a general sketch. We'll talk about end behavior and how I kind of came up with that, but we do know that it's going to cross through the x-axis. It's not going to bounce at those points. So now let's talk about end behavior. End behavior is essentially what it sounds like. It's what happens to the graph at the ends as x goes to negative infinity and x goes to positive infinity. So the first case we're going to look at is what happens if you have an even degree function. So this would be x squared, x to the fourth, x to the sixth, so forth and so on. What is going to happen if your lead coefficient is positive, is greater than 0? So these numbers are greater than 0, positive numbers. What our graph is going to happen as we go to negative infinity, like off to the left here, it's going to go up to positive infinity, and as we go off to positive infinity, it is also going to go to positive infinity. And in between, for instance, if we have something like x squared, it's just going to look parabolic. If we have something like x to the fourth, it might do kind of a wiggle in the middle. And so forth and so on. But it is always going to be pointing up to positive infinity in both directions as we go off to the ends. And if you think about it, if your lead coefficient is negative, then we're going to just flip this whole thing over. It's going to be going off to negative infinity in both directions. And again, if you have something, you could have some kind of wiggle in between. It's possible, depending if you have a higher order than 2, or higher degree than 2. So again, this is what happens when you have even degrees. It's rather symmetric, if you will. It goes either up to positive infinity with a positive coefficient or down to negative infinity with a negative coefficient. Whereas if you look at an odd degree function, that is going to be different. Odd degree, if you think about just a linear function, is going to be increasing from left to right when our lead coefficient is positive. And so it's going to be going off to negative infinity as you go to negative infinity, and positive infinity as you go to positive infinity. Again, this is when x is going to negative infinity, x is going to positive infinity for all of these. Same thing here. X is going to negative infinity, it's going backwards. X is going to positive infinity in the positive direction. Again, depending on what kind of function you have, it is possible that you might have kind of a wiggle in here if you've got something like a cubic or a quintic function, but it's always going to be kind of increasing when you have this left lead coefficient of a positive number. Again, if you flip this over, if you have a lead coefficient that is negative, then it is going to be decreasing from left to right. Again, you can kind of have a bit of a wiggle in here depending on what kind of function you're going for, but it is always going to be, again, approaching as you go to as x goes to negative infinity, this one's going to be going to positive. As x goes to positive infinity, the function is going to be going to negative infinity. So we're going to kind of put together everything we learned about degree, multiplicity, lead coefficient, and end behavior. A good place to start is to look at the intercepts, and for this we want to find the x and the y-intercepts. The y-intercept is usually the easiest to find. In this case, the x isn't too bad either, but the y-intercept, again, that's what happens when you plug in x equals 0. If you plug in x equals 0, you get 3 times 0 minus 7 times 0 plus 3 squared. So that ends up being 3 times negative 7 times 3 squared, which comes out to be negative 189, which is a large number, but that's okay. We can adjust our scale. Our x-intercepts are, again, when we set y equal to 0. So in this case, if y equals 0, then we have a root or an intercept or a 0, whichever you want to call it, at 7, and that has a multiplicity of 1 because there's just a coefficient of 1 there. And we also have a root of negative 3 from the second factor there, and that has a multiplicity of 2. And again, we know that since this is a multiplicity of 1, this is going to cross the axis, and a multiplicity of 2 is going to bounce or touch, but not cross. And the next thing that's kind of easy to find out, once you know those multiplicities, that you can find your degree by just adding those. 1 plus 2 is 3. Now this coefficient of 3 out front is going to help us with the lead coefficient, but it does not impact our degree, because technically this would be times x to the 0, and 0 is not going to increase our degree at all. So our degree is 3. Our lead coefficient in this case is also 3, because again, if you square this out, this would just be an x squared still. This would be times x, and the 3 here is what is going to influence this. So since this is positive and this is odd, then we know, putting kind of all of that together, that our graph is going to start from negative infinity and increase and do something, and then go up to positive infinity. So this is going to be kind of increasing from left to right. So let's go through and label our axes. Again, our x values here, we've got 7 and negative 3. So we might want to go by 2's here, or 1, make this a 1, and this a negative 1. Whereas that y-intercept, we got that negative 189. So I'm going to make this negative 100, negative 200, just so that we can fit everything on the graph. Same thing, kind of going up this way. Again, the x and y don't have to be the same increments, but everything on the x value has to be the same increments. Everything on the y-axis has to be the same increments. So we have our y-intercept was negative 189, so we'll put that somewhere pretty close to negative 200. And then we've got x-intercept, so that was that point there. We've got an x-intercept of 7, so we go forward 7, 1, 2, 3, 4, 5, 6, 7. And we have an x-intercept of negative 3, so we'll go back to that point as well. Again, we know that this is going to be starting off lower, since this negative 3 here, x equals negative 3, is the first point that we're going to come in contact with. We know it's going to be coming in this direction up to this point, and then we know it's going to bounce, so I'm going to kind of erase that so that it looks, instead of going through, it's a nice smooth curve, and it bounces, which makes sense because we have to go down to our y-intercept, and it'll cross through there, and then it's going to head over to this pink point here to our other one, and we know it's going to cross through the axis there. So again, it's not the prettiest curve, but it is just kind of a general sketch of what we could expect from a graph like this. Now I want you to pause the video and try example 8. So from this information, you should have a y-intercept of 0 and an x-intercept of 0. Those correspond to each other. Again, that x squared term is going to give you that. And then that had a multiplicity of 2, that x-intercept, so it's going to bounce. X equals 3 has a multiplicity of 1, so it will cross. It had degree 3, so it's going to kind of look like this because our lead coefficient was positive. So we're again increasing, we kind of bounce at that first point and then go back down and then back up again and cross through the x-intercept of 3. So it's really nice when everything's factored, or can be factored. There are times, though, when it doesn't work out so nice. In those cases, it's helpful to use the calculator. So before we get the calculator out, though, let's talk about the degree and the end behavior. So the degree in this case, again, the leading term has an exponent of 3. Our lead coefficient in this case is just 1. Again, kind of putting that together, we've had a lot of cubic functions. We're going to look something like this. We know it's going to look something like this. And then we're going to go to the calculator. So go ahead and get your calculator out. And we're going to graph this function. So we'll go to y equals x cubed plus 2x squared minus 5. And we graph this. And you'll see here we only end up with one real root. We'll talk about what this means in the next section as far as finding our imaginary roots, but in this case we only have one place where it crosses the x-axis, and that's here. Now if we want to find this point, we're going to go to second and then calc here. We're going to go to the second option 0. And what we're going to do is we're going to give it some bounds. When it asks for the left bound, that wants to be a little bit to the left. In this case, that's below. So we'll hit enter. And then it wants a right bound, so we'll go a little bit above the function in this case. And then it wants a guess, so we'll move back down to close to where it was, and we hit enter. And it tells us we have a 0 at 1.2418966. Now we had to give it those bounds because it's possible that there's more than one root, and it needs to know what interval to look in, so that's why we have to give it those left and right bounds. The guess just kind of helps it find the root a little bit faster. So in this case, we've got 1.242, we'll say. And again, this is an approximation. So if we wanted to graph this, again, we want to make sure we label our axes. I'll make this 1 and this -1 this time, similarly here. So again, if you were kind of looking, our y-intercept, on the other hand, is very easy to find. We just plug in 0, and we get 0 cubed plus 2 times 0 squared minus 5, which just comes out to be -5. So that will actually adjust our axes. Let's make this maybe 3 on our y-axis increment so that we can get to that -5. So we want to get to -5 is going to be our y-intercept. Our x-intercept here is that 1.24, so somewhere about here. And again, if you look here, it kind of goes up and then crosses there. So it's coming up and then dips to go through our y-intercept and then crosses. And so we'll talk about this a little bit more when we get to complex roots in the next section. So again, I want you to pause the video here and try this last example. So in this case, you should have found your degree was 4, lead coefficient was 3, kind of putting those together. We know we're going to be kind of going off in the positive direction for both positive and negative infinity. And then we found our y-intercept when you plug in 0 would be -4. X-intercept again on your graph, and this is again why it's important, why you need to pick the bounds, because in this case we had 2, so you need to make sure you surround this first point when you're finding your left and right bound. So it would be slightly up here, slightly down here, and then your left bound would be slightly below and your right bound would be slightly above for your positive x-intercept. We found the x-intercepts should have been -1.56 and 1.44. Both have a multiplicity of 1, so they're going to cross. And we end up with a graph that looks something like this. And again, that kind of wobble comes from the fact that we've got an x to the 4th instead of an x squared. So this concludes the video for section 16.1.